Hello, everybody. Welcome to our ongoing seminar series on analytics for a better world. We have been doing this for about every 2 months or so. And we are delighted today to have my colleague and friend, Nikolaos Trichakis, as our speaker today. Nikos graduated from MIT in 2011, and then joined Harvard University for a few years, and then we're very fortunate to attract him back in our faculty at the Sloan School of Management, where he's currently an associate professor in operations management. Nikos has a very broad interest, ranging from clearly healthcare, which is the focus of today, but many other areas: optimization under uncertainty, finance applications, operations in multiple other areas, and so forth. He's, I would say, in the last decade or so, his main interest has been what unifies all of this is the incorporating fairness and efficiency in a variety of systems. And today, and I would say he has a passion on these matters. I know that because we work on occasion closely on things. He will be talking to us today about a very, biased, admittedly, project on how to shape the national meaning US policy for transplantation for various organs, a topic that has been also present in while Nikos was doing his PhD and for the decade since then. I think he will be excited to see that our area of analytics has made a significant difference, and it will be implemented in the very near future, as I'm certain Nikos will outline. Please, if you have questions, either unmute yourself and write them, or send them through the chat. I will monitor that, but also you can wait until the end. Nikos can, is fine in either ways. Nikos, the floor is yours.
Okay, thank you very much, Dimitri. Thank you for the kind introduction, and thank you everyone for being here. I want to echo what Dimitri was saying, that this work is probably the one that I'm most proud of in terms of what I've achieved as an academic. It's a topic I've been working for many years. So that's, I guess, one part of it, but also the ability to work with a lot of practitioners coming from different fields, and being able to also implement stuff in practice. So I'm very excited to present this work. We've been doing it jointly with the United Network for Organ Sharing, or UNOS for short. Just as a brief background introduction for those of you who are not in the United States, UNOS is a governing body of transplantation activities in the United States. And for the last couple of years, it's undergoing a major overhaul of its organ allocation policies to basically make them more efficient, more equitable, and more inclusive. So with that in mind, we partnered with UNOS. So let me actually switch to my slides. And I'll be using my camera to project the slides. So maybe you can pin my video if you want. We'll basically have a larger share of the screen from my video. So as I mentioned, together with Ted Alexopoulos, Dimitris Bertsimas from MIT, Ted was a PhD student that we co-supervised with Dimitris. We partnered together with James Alcorn, Rebecca Goff, and Darren Stewart from UNOS. Darren has since then moved to NYU, but when we did this work, he was still with UNOS. And the idea was to conduct research and help UNOS in this major overhaul of transplant allocation policies to reshape national organ allocation policy. The outcome so far has been a novel analytical framework that we developed to aid policy design, and we applied this framework in collaboration with UNOS to design a new allocation policy for lungs, which will become national allocation policy in the United States in a couple of months. And we're currently continuing the efforts to design new policies for kidneys and livers. So it's been a very exciting journey for us. And what I hope I will do for the next 40 minutes or so is share some parts of it with you. And then maybe we can, have a discussion or address questions. Okay, so let me begin with a brief description of how organ allocation is organized in the United States. So roughly in the 80s, there was a congressional act from the US government that basically established a centralized program to coordinate all transplantation activities in the country. This has been named the Organ Procurement and Transplantation Network. And since its inception, this program has been run by UNOS, a non-profit organization. So basically, UNOS running the Organ Procurement and Transplantation Network in the United States is coordinating all transplantation activities in the country. And it's managing the national transplant waiting list. It's in charge of operations in terms of matching donors to recipients 24/7. Now, besides all these very important operations, UNOS is also in charge of national policy design. And they have certain processes in place to basically bring together multiple stakeholders from the transplant community in order to come up with prioritization tools or specific policies that basically dictate how organs are allocated to patients who have been waiting. Now, as you can imagine, policy design is a very challenging task. And, we're going to highlight many reasons of why this is the case. But, at a very high level, if you think about it, organs are often life-saving gifts. And the sad reality, at least in the United States and in many other parts of the world, is that there are just not enough of them. So there is shortage of supply. Just to give you some rough numbers, in the United States, there are currently more than 100,000 people waiting for an organ. And roughly 35,000 of them that are on the wait list get to have a transplant every year. And at the same time, 60,000 people join the list every year. And, if you look at the numbers, there is kind of a persistent mismatch in supply and demand, and these numbers have been kind of getting worse. So, in view of this acute shortage, allocation policies really have life and death consequences for the patient population. So, in view of that, UNOS policymakers strive to design allocation policies that are efficient. We want to make the best use of organs that are available. And, we can have a discussion about what best use means. But one way perhaps to think about it is we want to extend the lifespan of the patient population as much as possible. This is maybe one of the many metrics that we could use. But the main idea is, again, to kind of make the best use, some sort of maximize utility, let's say, in terms of how we use these organs. At the same time, there are also very important ethical and fairness considerations that arise. Are organs allocated across different groups in a fair way? We can think about different racial groups. We can think about different age groups, different genders, different geographies across the country. Are we making sure that once we allocate these organs, we are not disadvantaging any of these groups? And the considerations I mentioned is just a subset of fairness considerations that policymakers need to address. And the last 10 years or so, there's been growing evidence that despite all the continuing efforts to improve the policies and make the allocation system as fair and efficient as possible, that evidence suggests that there are still some inequities that persist. For example, there is some evidence that perhaps females are disadvantaged when it comes to liver allocation. There is also evidence that different geographies, when it comes to kidney allocation, might face very, very different wait times. So, you know, in view of all these concerns, UNOS decided 2 years ago to basically go through a major overhaul of all the policies. And this really has been a generational change. It has already started. And in the next couple of years, basically all policies will be migrated to a new framework that is called continuous distribution. So the idea behind continuous distribution will be to come up with a new framework that basically allow us to improve across these two dimensions that I've been talking. Make the system more efficient and make the system more equitable. So what I'm going to talk about now is I'm going to illustrate to you how the continuous distribution framework works and how, you know, important design decisions arise over there and how analytics could actually be impactful in addressing some of these problems. So the key idea behind continuous distribution is a simple scoring rule. So basically what we will do, and you know, this is an idea we routinely use in other resource allocation problems as well. We will identify some criteria for which we're going to award points to potential candidates on the wait list or recipients. And then we're going to award points according to this criteria. We're going to sum them up and we're going to come up with a score. And whoever scores the highest number in this score is the one who gets full, you know, highest priority. And that's the way we come up with basically a priority list. So here's an example where this composite allocation score, as we're going to call it, comprises three scores, three criteria: urgency, proximity, and whether the patient is pediatric or not. And you can think of different reasons for why, you know, these are kind of meaningful criteria. Of course, when it comes to organ allocation, if a patient, you know, is very medically faces a very medically urgent situation, they're about to die, you know, you want to prioritize them to some extent. You also want to give priority to proximity. You don't want to have organs traveling too far for many reasons that we're going to discuss later on as well. And you might also want to give priority to kids, to pediatric patients. So once you've identified this criteria, then you can come up with different weights that you assign to each criterion. These weights will tell you the relative importance of this criterion. And you can think of number of points per criterion, for example. And once you have that, you have this scoring rule that I've been talking about. And this is basically the main ingredient behind continuous distribution. Here is a particular example where we have 5 patients, maybe on the wait list, A through E on the x-axis. And then on the y-axis, you see an example of their composite allocation score. Broken down to these 3 criteria that I just talked about: urgency, proximity, and pediatric. And you see here that on this occasion, patient A is the one who has scored the highest. So they're the one that they're going to be offered the organ first. And, you know, interestingly here, you can see that patient A is not the most medically urgent patient. In fact, this is patient B. But because of proximity and because of patient A being pediatric, they end up, you know, accumulating the highest number of points. What this example also illustrates is really the 2 main components that we have to design carefully for a continuous distribution policy to work well. Namely, what criteria or attributes to award points for, but also how they should be weighted. the importance of the former, I think, is obvious. But I think this example also gives us some insights about why the weighting of the relative importance that we decide on these criteria is equally important in terms of the outcomes that we achieve. So, for example, on this particular occasion, had the weight on urgency been higher, or maybe the weight on proximity and pediatric being lower, then patient B could have been ranked first. So, basically you see that determining these weights actually has a first order effect on how we treat our patients and how we prioritize them on the wait list. What I'm going to talk about more is how to think about selecting the weights. Okay, thinking about how to select the attributes is really something that the medical community has a lot of insights about how to do. They understand when it comes to allocating different organs, whether medically urgency is very important or wait time is important, depending on the different organs. But as we will see, trying to figure out how to weigh these different weights actually poses a challenging problem also from an analytical perspective. Okay, so to illustrate to you why selecting these weights could be challenging, what I'm going to do is I'm going to guide you through the legacy policy design process that UNOS has been following for the past 10-15 years. And when I say UNOS, I'm using this term interchangeably with OPTN. Technically these are kind of OPTN committees, but since UNOS has been running the OPTN, that's why I've been kind of using these terms interchangeably. Whenever you hear about UNOS or OPTN, think about US policymakers. Maybe that's kind of the easiest way to parse these terminology that I'm using. Okay, so how have US policymakers thinking about policy design so far? At the heart of it lies a rather sophisticated simulation model that tries to predict outcomes given a certain policy that we have in place. And it does that using basically a lot of historical data. It's an event-driven simulation model that tries to capture a lot of elements of the transplantation activities process. So it starts from all the organs that have been procured. It has a lot of information on the wait list. It has information about how the health of patient evolves on the wait list, all based on historical data. And then there are models that tell us, if we use a policy that prioritizes patients in certain ways and results in particular offers as we simulate, what is the probability that a patient is going to accept an offer or not? If an offer is accepted, then we have a transplantation. If not, then it's offered to the second person on the wait list and so on and so forth. And then there are also models about post-transplant survival and whether some patients might release and things of that kind. So it's a very sophisticated allocation model. And how have US policymakers using this model? Well, they basically use intuition to come up with some design decisions. In our case, this will be the attributes and also a set of weights. We can come up with 5 or 10 candidate policies and then simulate them. Once we simulate, we can then observe or use this model to assess some predicted outcomes of interest. For example, we can see what the overall mortality rate is across the patient population in the country, what is the transplant rate, but also some operational questions on what is the transportation per organ. How far do organs travel? As I mentioned, this is important. But we also get to see a lot of interesting metrics when it comes to fairness and equity. These usually are measured in terms of discrepancies, by blood group, by age, by different gender, by different racial groups, and the like. And, once we simulate these policies, we might find some red flags. We might see that, a candidate policy that we simulated leads to unacceptable discrepancies across different racial groups. So what we do is then we go back and we try to fix this problem by readjusting the weights. So basically, the idea is to follow an iterative trial and error process where we kind of, use this feedback loop to improve the design. Now, if you think about it, this whole process is very daunting and challenging. First of all, coming up with guesses about what weights to use is challenging. It's very hard to predict, if I give you a set of weights, for example, what the outcomes are going to be. You can have a sense about some of the outcomes, but there are so many moving pieces that you kind of lose some visibility. There are just so many levers that you can tweak that once you kind of dial up one button, you increase one of the weight. This might have repercussions to different outcomes that are hard to predict. And also there are other issues over here. Of course, it might not be very intuitive for policymakers to think about weights to begin with, because it's almost like mixing apples and oranges to some extent, right? So you give 1 point for 1 year for weighting, and then you give 2 points, if you are close by. It's hard to think about these weights in this manner. So, working with UNOS, what we actually suggested was to flip this mindset. What we suggested was for policymakers to think about not necessarily on the left side of the picture that you see here, but actually begin from the right side, begin from the outcomes. So the idea is to now have some outcome-based policy design, so to speak, where what we do is we focus on outcomes. We have a discussion about, what do we want to achieve? Of course, we want to, minimize mortality, for example. We want to increase life expectancy, but sometimes this trades off with equity considerations, as we're going to see. So how exactly do we want to trade this off? What exactly do we want to achieve? This is a discussion that is much better suited for policymakers. And, once this is done, then what we can use is analytics and optimization to come up with a design decisions. This mindset also improves for a much better search of the policy space. We no longer think about, a small number of candidate policies, but we use optimization to search through the entire policy space. In this case, we search through the entire set of all possible weights, so to speak. So that will also allow us to get to, much more efficient policies as we're going to see. And also important trade-off analysis that I'm going to illustrate. Okay, so let me take some time to introduce the core idea behind the analytical framework that we designed to facilitate this outcome-based policy design process that I illustrated. So the idea is we have outcomes we want to achieve, and then we use optimization to be able to come up with design decisions. This is basically an inverse control problem. Okay, so the idea is that there is a set. I'm going to use some abstraction now to better illustrate the ideas. So the idea is we have a set of feasible policies, pi, and we want to pick a policy from that set. And we care about multiple objectives. So Fi over here is going to encode the ith objective or outcome that we care about. This will map a policy that we pick to a number. Okay, so this could be, for example, the mortality of the policy that we pick, or this could be a measure of a discrepancy between different racial groups of the policy that we pick. The catch here is that this mapping is very complicated. We don't have a formula for it. It's not given a closed form expression or something like that. It's evaluated through a costly simulation model. Now, we have certain target outcomes. So for these outcomes, let's say there are n+1 of them. Let's say that outcomes 1 up to n, we want to minimize, and we set some targets. So we say that T1 or less is the acceptable range for the first outcome, and so on and so forth. And let's assume without loss that the 0th outcome is the one that we want to minimize. So this fits with exactly what I was trying to explain before, that what we do is we're saying this is the outcome we want to achieve. Let's find a policy that comes as close as possible to achieving that. So basically, you can now write this mathematical optimization problem that you can see at the bottom, where you want to find a policy pi that will minimize F0, subject to hitting the outcomes you prescribed. Fi of pi should be less than or equal to Ti, and the policy should be feasible. Now, the problem with solving this optimization problem, of course, is that F is a black box process, so to speak. It's costly to even evaluate it. So how can we go about approximating this optimization problem, or finding an approximate solution to this optimization problem? We basically followed the following process. We used a mix of simulation, machine learning, and optimization to come up with surrogate models, which we then feed back to the optimization process that will allow us to get these approximations. So, more concretely, what we do is the following. We create a training set by sampling policies at random. Okay, so think about using some sampling procedure, and you come up with pi s, which is a random policy that you come up with. Now, what you can do is you can simulate these random policies and record the outcomes that you get. So YIS will be the ith outcome of the S sample that we have in our training set. Now, you can now treat these Ys as basically the dependent variables in a machine learning model, and the policies pi as being the dependent variables. Sorry, the independent variables. Okay, so basically, if your policy is parametric, this fits directly then into a machine learning framework. And what you can do is you can use a machine learning model that will then allow us to predict for a policy that we have not seen, what would the expected outcomes are going to be. So I'm going to denote with F tilde this surrogate model that will try to make this prediction. So given a policy now that we might not have not seen, pi, Fi tilde of pi is the ith outcome value that the machine learning model predicts for this ith outcome. And hopefully, this approximation will be close to the true value. And if that is the case, and on top of that, the machine learning model is amendable to optimization. So for example, it's MIP representable. If we replace now in the original problem, the simulation model or the black box function F with its approximation F tilde, what we get is now a tractable optimization problem that we can solve multiple times for different targets and see how well it performs. Okay, so that's kind of the core idea behind the analytical framework that we designed, that really facilitates this idea of outcome-driven policy design. Let me illustrate this with an example, probably the simplest example that you can come up with. Let's say that you want to design a policy that is parameterized by a simple vector. This could be a continuous distribution policy, going back to what I was discussing before. This could be literally the weights of the attributes that we want to pick within organ allocation. So pi, in other words, is just a vector, a k-dimensional vector in this example, if you look at the first row. So what are we going to do is we're going to sample basically k-dimensional vectors at random. We're going to simulate them. We're going to simulate the associated continuous distribution policies. We're going to record the associated outcomes y, I of s. And then what is the simplest, let's say, machine learning model? Let's say a linear model. So a model that will tell us, given a policies, i.e. a vector w in this case, what is the ith outcome? Well, let's use a linear relationship over here that you can see. Basically, A transpose IW plus BI is the simplest linear relationship we can use to make these predictions. So if this model provides a good fit, basically what we're going to use is some sort of a regression, really, to find the weights that give us the best fit. So find these coefficients A and B that will minimize this loss over here. And if that fit is well, and we have credible approximations, then we can go back to the optimization problem and replace all the F mappings with these simple linear relationships. And now we just have a simple LP to solve every time we want to design a new policy. So we pick the targets we want to achieve, and this problem will give us the weights that come as close as possible to achieving these weights. Okay, so before I go into how we applied this for the transplant allocation example, just few remarks. The model I just described using this abstraction is fairly general. You can think of using it in situations where you face a multi-objective optimization problem. So you care about multiple objectives, and critically evaluating these objectives is costly. So it comes to, let's say, a simulation model or other processes that you cannot repeat in an efficient way. And the moment you have a parametric policy that you are trying to look for in order to solve this, in this case, inverse optimization problem, well, you can use this framework. In resource allocation, this could be very useful in other settings like public housing or vaccine allocation, because again, you kind of face similar problems over there. In terms of the methodology itself, there are many ways you can improve it. You can make the sampling smarter and things like that, but there are still limitations. It will only work well when the fit that you have is good. So you might be tempted to use, more sophisticated machine learning models, not just linear functions, obviously, but maybe decision trees and neural networks. And this is fine as long as the choice of the machine learning model that you pick is one that is amendable to optimization. So, for example, as long as it's parametric and mixed integer representable, this still fits in our framework. Not all machine learning models obviously fit in this framework. But decision trees still fit in this framework, and feed-forward neural networks also fit as long as you have linear activation functions. And then some limitations. Of course, this model is as good as the underlying simulation model that you have. And you also have to be careful. Sometimes optimization is known to exploit inaccuracies, in the learning model as well. Okay, so let me now go to discussing how we applied this for the lung allocation process. So what we did is we worked closely with the lung allocation committee to basically address the following question. The committee had identified 6 criteria for which they wanted to award points for lung allocation: proximity, waitlist survival, post-transplant outcomes, biological disadvantages, whether you're primary living donor, and whether you're pediatric or not. And the concrete question we tried to address was how to pick some of these weights. So this fits directly into the framework that we developed. So what we did was we sampled a lot of different policies, and then we fitted piecewise linear functions. We used the same simulator that UNOS is using, and the piecewise linear model we developed had very, very good accuracy. The out of sample R square was more than 92%. So we had, good, basically we had very good approximations that we could fit in the optimization model that we had. An important part of our work with policymakers was making this framework available to them. So what we did was we developed basically a website, a dashboard, an interactive design tool that allowed policymakers to explore and use this framework to design policies themselves. And this allowed them to actually find and look at very interesting trade-offs. So let me show you how the framework worked, and then I'm going to talk about some of the important frameworks that came out of using this tool. So in the tool, you would pick an objective, that's the drop-down menu on the top, and then you would use these sliders to basically pick different targets over here for transplantation distance and different transplant rate disparities. So basically, you would pick these outcomes that I was talking about. And then by hitting the optimize button, you would get a report on whether you hit the different targets that you picked or not. I'm going to actually show you a quick video over here that illustrates the use of this. Ted, our student who helped us a lot, obviously, developing this, is going to provide this demonstration. So let me actually take a moment to launch the video.
A policymaker could start off by posing the following hypothetical. What sort of continuous allocation policy most reduces mortality while keeping organ transport burden within 20% of the status quo? So on this first user input page here, we can specify this in terms of an objective to optimize, in this case, minimize the total number of deaths over the simulation horizon, as well as an upper bound on the median organ transport distance, which we can set to a value of about 200 nautical miles per organ, corresponding to an increase of about 20% relative to current policy. And by hitting the optimize button, within seconds, the tool has come up with a set of scoring factors and weights, which best satisfy our criteria. It also produces predictions on a range of allocation outcomes that might be of interest to policymakers. So you'll note, in fact, that the proposed policy has reduced the total number of deaths over the simulation horizon from 1,077 under current policy down to 932, a reduction of about 145, while also maintaining median transport distance at the desired level of 200 nautical miles. Now, of course, a policymaker could actually look at this outcome table and also observe that the policy has the undesired effect of decreasing pediatric transplant rates from about 3.96 transplants per patient year down to 2.58 transplants per patient year. And so they might want to go back to the user input tab and place an additional constraint on this outcome, placing a lower bound at 3.96 or about 100% relative to current policy. And by hitting the optimize button again, we get a new set of scoring weights and factors, as well as a new set of predictions on outcomes, which now we see satisfy both constraints, 200 nautical miles and 3.96 transplants per patient year, while maintaining the reduction of about 140 deaths over current policy.
Okay, and basically, what you can see with this is that there are a lot of moving pieces, right? So you fix one outcome and then you realize that it trade-offs with another. So once we made this tool available to policymakers, they were able to identify some very important trade-offs that were underlying the choice of some of these weights. So what I'm going to illustrate to you for the next 10 minutes or so is how we analyzed the selection of the proximity weight and the selection of the pediatric weight by analyzing certain trade-offs. So let's think about how to pick the proximity weight. So we want to award points for patients who are close to the donor hospital. We want to do this because having organs flying, for example, around the country or traveling a long distance is undesirable. The reason is that the longer the organ stays outside of blood circulation, this is called cold ischemia time, its quality deteriorates. So basically, we want to have a short time between procurement and transplantation, and traveling doesn't help. There's a flip side, although, to that. If there is a medically urgent patient who is far away, well, if we don't travel far away, then we're going to have deaths occurring. So basically, you can see an important trade-off over here that has to do with distance and mortality. So the question is, how much emphasis should we put into local transplantation with the expense of perhaps having more deaths? So let me illustrate to you the analysis that we did to help inform the choice of how much emphasis to put on this way. So what I'm going to use over here is a trade-off analysis. On the x-axis, we have median transport distance in nautical miles, and on the y-axis, we have waitlist mortality over 1 year for patients who are on the lung transplantation waitlist. Now, each green dot that you see over here is a policy that we designed using our tool, and it's plotted depending on the median transport distance that it achieves and the mortality that it achieves. And I have also plotted the current policy that was being used before continuous distribution was introduced as a black dot up there. So, first of all, what do we observe? We observe that as the median transport distance of policies increases, mortality goes down. And this is intuitive. The broader distribution of organs we have the ability to reach out to medically urgent patients, perform the transplant, and basically save their lives. The more emphasis we give to local transplants, i.e. we go to the left of this graph, transportation goes down, but mortality goes up. And the question is, how do you navigate this trade-off? First of all, using our tool, we were able to find these policies that form a Pareto frontier. Basically, these policies achieve the minimum mortality for a certain transplantation distance that you have. We did this by using our tool of minimizing mortality subject to a particular transport distance not being higher than a target, which we varied so that we get this frontier. So this allowed us to precisely highlight this trade-off. Now, if you look at the top of the graph, I'm plotting the proximity weight. So an interesting thing that came out from this analysis is the fact that 10%, a weight of 10% appear to be roughly a sweet spot. Look at what happens if you have a weight that is higher than 10%. So you are to the left. Basically, you have a steep increase into deaths. Yes, you are reducing transportation distance, but for every mile that you save, this translates into a lot of lives that are being lost. On the contrary, if you look to the right of 10%, you are now starting increasing transportation distance, therefore decreasing also the quality of the organs. And this doesn't really translate to a huge gain in terms of how many lives you're saving. So there seems to be an inflection point around the 10% area. And this analysis was able to quantify this and suggest that a weight of roughly 10% was kind of a sweet spot as you were thinking about this trade-off.
Nikos, may I ask something?
Yes, please go ahead.
Hi, my name is Caroline, and I was wondering, you said that if the organs are not in blood circulation for a while, the quality deteriorates, and I imagine that also the survival probability of the receiving patient declines. Is that not in your simulation model?
Great question. That is in the simulation model. The reason I emphasized only the former Caroline is that the time scale is a little bit different. You're right. Health deteriorates, but usually health deteriorates, within a month or within weeks. Now we're talking about hours, right? So now we're talking about the procurement has happened. Do we assign it locally? That's like 1 hour, or do we travel and we go to the middle of the country? That's now 12 hours. Okay, so that's why for this time scale, I focused more on the.
Yes, I see what you mean in terms of the patient while waiting for the organ doesn't deteriorate that much in a few hours. But the probability that the surgery is successful and the organ is accepted into the body, etc., is that affected?
Yeah, that's right. That's all baked in the model. Yes, right. That's baked in the model.
Thanks.
Yeah. Something else that I wanted to highlight over here is also the gap between the current policy and the efficient frontier that is also interesting to look at. There are two reasons that we are able to improve so much compared to current policy. The first one is that we're using, first of all, a different class of policies. Okay, so the green dots are continuous distribution policies. The current policy was not a continuous distribution policy, was basically a tiered system. It was not as flexible. It didn't give us the same degrees of freedom. So we already get some benefits. We are basically saving almost 100 lives. That's roughly 20% mortality reduction without increasing the transport distance further. Okay. So we're getting these benefits because we're using a continuous distribution policy, but also because we're using a sophisticated optimization process to find a really efficient policy. So we're kind of improving the policy design process as well. Okay. Let me now also show you some analysis that we did. So, by the way, these are some sensitivity analysis that we did. This is the same graph. The only difference that on the x-axis we're now measuring the percentage of organs flown. So a similar metric that has to do with distance. And you see that again, 10% seems to be a sweet spot. So this was kind of some robustness sensitivity analysis to do because there are different ways to measure transport distance. So this kind of gave us confidence that 10% was kind of the right way. Let me switch focus now to pediatric analysis. The question is how much emphasis to give on pediatric patients. Similar type of plot and analysis. On the x-axis, we have the pediatric weight, how much emphasis we give to pediatrics. On the y-axis, we have the pediatric transplant rate. So how many, basically a measure of how many organs go to kids 12 years or younger. And again, we used this optimization framework to find the Pareto frontier. What we are looking at here is the minimum transplant rate, so a guarantee on the transplant rate that pediatrics will get as you vary all the other weights. And what this was showing was that as you increase the weight on kids, of course, transplant rates increase because you give more priority to them. But after some point, roughly 20%, it saturates. So you don't need to increase the weight further than that. So 20% was kind of the sweet spot that came out from this analysis. These were like two concrete analyses that I showed you. We did others, but I hope they illustrate the importance of doing this trade-off analysis once you deal with multiple objectives that you don't necessarily know how they trade off with each other. So in the end, the policy, the committee, the OPTN Lung Allocation Committee for these two weights that I discussed, picked precisely the ways that I illustrated. So this is the new allocation policy that is going to become, you know, the national allocation policy in the United States in a couple of months. The weights were picked precisely using this analysis, or were in line with what we suggested. And as I mentioned, we are now extending these efforts. We're working closely with the kidney allocation committee and the liver allocation committee to help design these policies as well. So I want to thank you for your attention. I'm happy to take any questions. In terms of, you know, summarizing, I think the importance of this work is, I think, a useful framework that you can use when you face important policy decisions in resource allocation, because these are situations where you have to deal with multiple objectives. You don't exactly know how they trade off with each other. Evaluation is costly. If you give me a policy, understanding you know, how it will affect different outcomes is not easy. And I think this way of thinking about from outcomes to policy design and using analytics to make predictions about how a policy affects outcomes could be powerful and useful, with, you know, certain limitations that I also tried to highlight. So thank you for your attention, and I'm happy to, you know, answer any questions if there are any.
Thank you very much, Nikos. I have one question. This is very interesting and very important. And I'm wondering, of course, it can always be more complex. And
Yes.
You are, I know, showing us only a little bit of all that you have done. But within pediatrics, for example, do you also consider other variables within it? Like also, it's not equally distributed, right? Within pediatrics itself, the gender or the race.
Yeah.
Would that also?
Right, absolutely. That's a great question. Thanks for bringing it up. So when I was showing these policies, right? So when we design them, we include in the optimization model constraints that tell us, don't mess up different discrepancies. Make sure that distribution across racial groups is, you know, within these boundaries, and so on and so forth. So yes, this is actually an important point to make. There are a lot of details that are kind of hidden over here.
Thank you.
Nico, I was wondering if you could outline where is this effort with respect to implementation?
So as far as you know, the lung allocation process that we discussed, it has concluded. You know, using this analysis that I showed, the committee picked these particular weights, this particular policy that you see on the screen. This was approved by the board of directors of UNOS and OPTN roughly a year ago, and it's going to be implemented in practice in a month.
And other organs?
And then we are actively working with the kidney allocation committee, kidney policy allocation committee. We are doing similar type of analysis. The current timeline is that probably there will be a new policy that will be designed next year. The problem over there is much more complicated. There are roughly close to 14 weights as opposed to 6 weights. So as the dimension grows, you can imagine that the need for these tools is higher, because it's hard to predict you know, changes when you have so many decision levers. Yeah, and after that, we've started talking with the liver, you know, policymakers in the liver allocation committee as well. So hopefully this tool can help reshape. That's why we picked this title, hopefully this tool will help reshape the entire spectrum of allocation policies in the country. It has already done it for lungs, and hopefully it will help also with others. And it's currently doing that.
Can I ask a question?
Of course.
Well, thank you very much. Really, I enjoyed the talk,
Thank
and
you.
congratulations to you and Professor Persima. So I wonder how often would it be good to update the weights?
Yeah.
Because is it every month? Is it every year?
That's a great question, Mehmet. In fact, one of the appealing things of the continuous distribution is that you can change this weight easily, right? It's a flexible program, and time will tell. What will happen is that these policies are going to be implemented. They're going to be closely monitored, and within a year or 2 years, we will observe outcomes. Have they matched with our expectations? If not, we're going to update these models, and we're going to rerun all this analysis, and we're going to update the weights. If not, if they've matched what we expected, then there is no need to update. But the key is that the ability is there.
Great, thank you.
Can I also ask a question?
Of course.
Nico? Thank you for the talk. Really interesting. So I was wondering, you talked in the beginning about this fairness thing that you want to incorporate, but in the end you have these targets that you still need to set, right? Doesn't this have a big influence on how fair a current distribution of weights is in the end? And my question is, do you have any insight in how you might tackle this issue?
Absolutely, great question. And the way we thought about this, and we did analysis, was we used trade-off curves of that kind, where here we are measuring on the y-axis maybe an efficiency metric. How many lives do we save as we transport distance further and further out? You can think of having on the y-axis another metric that has to do with fairness, for example, geographic disparity. So how different is your experience if you're in a particular geography as opposed to another? You can think about some areas being more disadvantaged than others. And what we did was analysis of this kind, where on the y-axis, we had a metric of geographic disparity. Okay, and you would see that as you increase distance, as you have a broader distribution of organs, these disparities go down, because you basically almost kind of treat the entire country as one wait list, so to speak, right? But as you put more emphasis on local transplants, geographic disparities might increase. So to address fairness questions, we did analysis of that kind that allowed policymakers to again understand, how much do we gain by increasing distance? By how much do we gain on the fairness front? So this allowed them to actually quantify these gains based on the metrics that you would pick. Okay, so a very important part.
Thanks.
Well, given the time, I would like to thank Nikos for a great talk, and we are going to continue our seminars in about 2 months. We'll send an appropriate announcement at the time. Thank you all for coming. Thank you, Nikos, for the presentation today.
Thank you. Thank you, everyone.
Thank you.